Walk into, a high-end sports bar or one of those multi-million-dollar smart homes, and you'll see dozens of screens flawlessly synced in 4K.
Oh yeah, they look incredible.
Right, but you never see the actual brain making it happen behind the scenes. So today, we are opening up that brain. We're doing a deep dive into the specs for the Atlona AT-HDR-H2H-88MA.
Which is quite a mouthful.
It really is. It's a $2,950 4K HDR matrix switcher. And the mission for you listening today is to help decode this intimidating spec sheet. We want to reveal why this specific 1U rack-mountable box is the hidden command center behind all these video networks. So, okay, let's unpack this.
Do it.
I think we should bypass the basic what is a switcher question, because this isn't just a simple splitter, is it? It's more like a hyper-efficient digital traffic cop.
That's actually a great way to put it.
Yeah, so is this essentially routing up to 8 distinct inputs independently to 8 different displays all at once?
Exactly. It's a dynamic routing engine. But what really stands out on this spec sheet isn't just the routing itself. It's the HDCP 2.2 compliance across all those ports.
Right, the encryption standard.
Yeah, and that matters because you aren't just passively passing a signal along. You are continuously managing, up to 64 potential encryption pathways in real time.
Wait, 64 pathways. Maintaining those strict handshakes across 8 distinct endpoints without screen dropouts, that has to require a massive processing load.
Oh, it's a tremendous processing load. If one display drops its handshake, a lesser switcher might just, blank out the entire network while it renegotiates.
Which would be totally unacceptable in a commercial setting.
Right. But this unit maintains those encrypted keys independently for each zone. So a source change in one room doesn't interrupt the Dolby Vision feed in another.
Okay, here's where it gets really interesting. Because we look at the raw data traveling across this matrix, we hit a physical bottleneck. The spec sheet loudly boasts about an 18 Gbps bandwidth capacity per channel.
Yeah, that's a big number.
It is. Now, I have to challenge this 18 Gbps number. Netflix 4K streaming only requires about, 15 megabits per second?
Right, around there.
So are they just inflating the specs on the box to justify a $3,000 price tag? Is that much bandwidth actually necessary for a home setup?
Well, what's fascinating here is the massive difference between highly compressed internet delivery and raw, uncompressed local rendering.
Okay, go on.
Netflix relies on heavy compression, but when you're routing pristine 4K video at 60 Hz with a 4.4.4 chroma subsampling rate, you aren't streaming a compressed file anymore.
Oh, I see.
Yeah, and you add in dynamic formats like HDR10 and Dolby Vision, and you are literally moving raw pixel data. You need every bit of that 18 Gbps pipeline.
Wow, right. And routing 8 of those 18 Gbps streamed simultaneously inside a slim 1U chassis, that's 144 Gbps of total throughput.
It is.
That has to generate an insane amount of heat and processing friction.
Exactly. Managing that much uncompressed data requires serious thermal management, plus incredibly precise internal clocking to prevent signal degradation.
Which makes sense of the price tag.
Right, that is what you're actually paying for. It's the hardware's ability to sustain those maximum data rates continuously across all ports without the processor thermal throttling or, introducing any latency.
Okay, so we've successfully routed these massive uncompressed video signals to the displays, but TVs generally have terrible built-in audio processing.
Oh, absolutely terrible.
Yeah, and relying on them to pass audio to a separate system can create a huge bottleneck. Which brings us to the HDMI audio de-embedding feature. So what does this all mean?
Well, it's a crucial feature.
To me, it kind of sounds like peeling a banana, right? Like using a prism to split a specific spectrum of light off from a single beam. You extract that complex audio data locally at the rack and route it directly to the whole house sound system while the pure video signal continues onto the TV.
That prism mechanism is exactly what's happening. I love that analogy.
Thanks.
Instead of forcing the display to receive the complex audio and rely on audio return channels, which honestly can introduce latency and format limitations.
Yeah, those are always a headache.
Right. So this box extracts a dedicated, unbalanced analog audio feed right at the source rack for each of the 8 inputs. The local amplifiers take over the sound, and the screens just render the picture.
Which completely eliminates a nightmare of audio return wiring behind the drywall.
Exactly. It simplifies the entire physical layer, and they applied that same logic to the control layer, too.
How so?
Well, you're managing 8 zones, so rather than relying on complex third-party control processing just to turn the TVs on, The switcher uses independent CEC display control and a built-in GUI web server.
Oh, wow. So the matrix itself natively commands the displays to wake up or change states.
Exactly.
So to bring this all together for you listening, this box is far more than a simple AV accessory. It is a foundational command center doing heavy computational lifting. It manages uncompressed bandwidth, independent encryption keys, and system-wide CEC triggers, all to deliver a flawless visual experience.
Yeah, and if we connect this to the bigger picture, it really highlights a structural threshold we are approaching in physical architecture.
What do you mean?
Well, think about it. If uncompressed 4K video at 60 Hz is already maxing out an 18 Gbps pipeline today, how will the physical copper wiring hidden inside the walls of our homes need to evolve when 8K, 120 Hz, or, uncompressed spatial video technologies become the standard?
Oh, man. That is a massive infrastructure bottleneck just waiting to happen.
It really is.
Definitely something to think about the next time you marvel at a perfectly crisp screen. Well, thanks for joining us on this deep dive, and we'll catch you on the next one.